Okay, this will be the lecture for Chapter 4, where we talk about Newton's second law of motion. Up until this point, we've talked about several key concepts. We've talked about forces, we've talked about acceleration, we've talked about velocity, and we've talked about position. So now what we're going to kind of do is we're going to link these guys together. We do know that if the sum of the forces on an object are equal to 0, then it's not going to accelerate. Today we're going to talk about what happens when the sum of the forces is not equal to 0. It turns out the forces are going to cause acceleration, which is going to be a change in velocity. We'll talk about one special type of force that's called friction. And we'll talk about finally what weight is. Weight's going to be a force, and that's very, very, very different than mass. And we'll kind of build our way up to Newton's second law of acceleration, which essentially says force is equal to mass multiplied by acceleration. We'll talk about the case of free fall, and then we'll talk very briefly about the case where there is air resistance or non-free fall. Now, I'm probably not telling you anything new when I tell you that a force is going to cause acceleration. Let's think of your car for a second. If it's just sitting there, then it's just going to sit there. But as soon as you apply a force on it, then it's going to accelerate. And if you were to have your same car, and you were to stomp on your gas pedal twice as much, so you're going to produce twice as much force, then you're going to accelerate faster. So what we can kind of say is if we want to increase the acceleration of an object, increase the net force on the object. So we're going to say net force is proportional, or the net force is proportional to acceleration. That little squiggly right there just kind of means proportional to, which means kind of goes with. So as the net force goes up, then acceleration also goes up. Now, I do want to talk about one very, very special type of force that's going to act upon pretty much every object, and I've already kind of used it a couple times. That's going to be an object's weight. An object's weight is going to be a force, and weight and mass are actually very different, even though they're used interchangeably sometimes. Now, what an object's mass is going to be just a property of an object that has mass, and it's just kind of a measure of inertia, or how much it resists acceleration, so kind of how sluggish it is, and just how easy is it to start an object, to stop it, or change its motion in any way. And a weight is going to be a force on an object that's due to gravity, and yes, weight does depend on mass. It turns out that weight is going to be equal to an object's mass multiplied by its gravity. So if I had an object, say, that was 10 kilograms, then its weight would be 10 kilograms multiplied by gravity, which is going to be 10, so its weight would be 100 newtons. Now, I think that units are one reason why we often confuse weight and mass, especially in the English system. Again, mass is just going to be how much inertia an object has. More mass means more inertia, and the unit for mass is going to be our old friend the kilogram. Now, weight, again, is going to be a force, which is going to, again, be mass multiplied by gravity, and yes, it does depend on mass. The unit of all forces is going to be a newton, and in the English system, we're used to this, unit of weight being a pound. In the English system, the unit for mass is going to actually be something called the slug, and I think that's why we never really think about that much in the English system, because we never talk about mass, we always talk about weight. So just think about the relationship between mass and weight as you pause and just try to solve this problem. If we half an object's mass, I'll remember that weight is equal to mass multiplied by gravity. So as this guy is halved, then this guy is also going to be halved. Just to perhaps give you a better feeling for mass and weight, a kilogram is going to weigh 10 newtons, or actually 9.8 to be precise. Relating kilograms to pounds, we know that a kilogram is actually going to be 2.2 pounds, which is also going to be 10 newtons at Earth's surface, and we know that 1 pound is also going to be 4.45 newtons. So I have just kind of a little bit of a demonstration on the difference between mass and weight. We kind of in everyday conversation, you can use them interchangeably, but we can definitely not in a physics classroom. They do rely on each other, but mass is far more fundamental, and I have a little bit of a video that discusses mass versus weight. So consider this. You pick up a basketball on Earth, you're going to feel its weight. Its mass multiplied by gravity. You pick up a bowling ball, it's got more mass, it's got more weight. Gravity is the same here on Earth. You go to the moon, gravity is about a sixth on the moon as what it is here on the Earth. So you pick up these two guys, and they're going to feel a lot lighter. Their mass hasn't changed, however, gravity has gone down. If you really want to determine the mass, what you have to do is you have to shake it. How much does it resist your acceleration? If you were to shake that basketball here on Earth and the moon, it's going to resist your acceleration the same. Bowling ball has a lot more mass to it. It resists it. You can kind of see how I'm struggling there. Now, I do want to distinguish a little bit about mass and weight. If you were to consider this setup right here, and if you pull the string down slowly with your hand, it turns out that the top string is going to break. If, however, you pull down quickly, then the bottom string is going to break. And this kind of comes back to the difference between mass and weight. So if you think about it, this top string has some tension in it. It's got all this mass that is pulling down on it. This bottom string does not have all that mass pulling down on it. So the tension in the top string is larger than the tension in the bottom string. So as you slowly pull down, then we're going to have not just the weight of this ball, you're also going to have the tension from the hand. So this is actually going to best illustrate the weight of the ball. However, if you pull down quickly, then the bottom string breaks. This is actually going to best illustrate the mass of the ball. Now, why is this? Well, think about it. This ball is big and heavy, and it has a lot of mass. Lots of mass means lots of inertia. So before the tension in the top string can become large enough to break, there's too much tension in the bottom string simply by the fact that the ball has mass. Now, let's kind of shift gears a little bit and think about how mass is going to resist acceleration. Now, we all know that if we have our pickup truck and we try to accelerate it, then it's going to accelerate. But as we maybe put a big load of bricks or rocks in the back, then the truck has roughly the same amount of force, and it's just not going to accelerate nearly as much. So if an object were to double its mass, then the acceleration is actually going to be half. If we loaded up the truck to 3 times its mass, which I wouldn't recommend, then it's going to be about a third of the acceleration. So acceleration is going to be inversely proportional to mass. Again, that means proportional to, and this is an inverse. And what this kind of says, as the mass kind of goes up, then you're dividing by a larger and larger and larger number, so the acceleration is going to go down. And Isaac Newton was the fellow that first kind of realized that if force is proportional to acceleration, and acceleration is proportional to 1 divided by mass, he said, hey, we can go ahead and we can put these guys together, and we can say that an object's force is going to be equal to its mass multiplied by acceleration. And we call this relationship Newton's second law of motion because it came after the first one, and this just kind of says in text everything that I said on the previous page, that the net force on an object is going to be equal to its mass multiplied by its acceleration, and this kind of makes sense. If we were to apply a big force to an object, so the force goes up, then we would expect the acceleration to go up. However, as we make an object more and more and more massive, then we would expect the acceleration to go down for the same amount of force. We can kind of rearrange this guy to get the acceleration, and the acceleration is going to depend on the force and the mass. So if we were to double the force on an object, so increase that guy, then the acceleration you would expect also to go up. So you would expect it to be double, so it would be 2 times as much. As the mass of an object goes up, kind of like I said, if it were to double, then you're essentially dividing by a much larger number, so the acceleration would be half as much. We'd expect the acceleration to go down. So let's just kind of look at this conceptually, remembering that an object's acceleration is going to be the force divided by the mass. If we have some force that's going to accelerate the brick at some rate, then we would expect if there's 2 bricks that we're essentially doubling the mass, so to accelerate half as much, and 3 bricks would accelerate as third as much because we have 3 times the mass, we're dividing by a larger number. If we use 2 hands on the bricks for just having 1 brick, then the force has now doubled, so it should produce twice as much acceleration. Now, if we were to double the force and double the acceleration, or double the mass, kind of in this example right here, we expect the acceleration to be the same because we've essentially double this guy and double this guy, so the acceleration is just going to be what it was initially. Let's just get a little bit of practice working a force problem, so go ahead and give this a try on your own for a second. So we're given that the truck's acceleration is going to be 1 meter per second squared, and we know that it has a mass of 2,000 kilograms, and kind of what we're looking for is what is the force that is required. Well, force is going to be equal to mass multiplied by acceleration, so it's simply going to be 2,000 kilograms multiplied by the acceleration, which is 1. So it's going to be a force of about 2,000 newtons. Again, just a little bit of practice. Suppose we have a cart pushed along the track with a certain force, and if the force remains the same and the mass is decreased, well, we would expect that the acceleration to double, because we're essentially lowering the mass, so it should be easier to acceleration. Now, on this question right here, give yourself a second and try to solve it. So we're going to push a cart in such a manner that twice as much force acts on it, but the acceleration remains the same. The only explanation for this is going to be if the mass of the cart is also doubled. Remember, acceleration is going to be equal to force divided by mass. And if I were to say, okay, you know what, I don't even know what the force is going to be initially. Suppose I'm just going to say the force initially is equal to 1 and the mass is equal to 1. Then I would say my acceleration is also going to be equal to 1. And what I've been told is twice as much force is going to act on it, so this new force must be equal to 2. And I know the acceleration is going to be the same, so the acceleration is still going to be equal to 1. So what I'm kind of left with is acceleration 1 is going to be equal to force, which is now 2. And what we're looking for is this new mass. Well, this mass obviously has to be 2, because 2 divided by 2 is equal to 1.